Dear students, welcome to my channel. Topic of this video is Introduction to Image Processing. This is the fourth video on this topic. In this video, I am going to discuss sampling and quantization and resolution concept. Now let us start. Transforming an analog image into digital one requires two key steps. First is sampling and second is quantization. Both processes work together. Sampling converts optical signal to electrical signal and quantization converts electrical signal to digital signal. Sampling digitizing the coordinate values. Sampling discretizes space and captures the image at a specific points. Quantization digitizes the amplitude values. It discretizes intensity and assigning digital values to those captured points. Now this is a scene element which we want to capture and convert into the digital form. Now light capture. The camera lens focus light rays from the scene onto light sensitive sensor. So in sampling, this set of sensor array is used, and whatever the energy radiated from that object in the form of optical is converted to electrical. Light to signal conversion. The sensor converts the captured light into electrical signal. Each pixel on the sensor corresponds to specific point in the image. So when this grid is very fine, so we are getting more number of pixels in an image, that is nothing but more samples. Signal processing. The electrical signals are processed by the camera image processor unit to adjust the factor like color balance, exposure and white balance. This is only to capture the good quality of the image. Now digitizer. The processed electrical signal are converted to digital format. Now see, this is the image we want to capture. So after the conversion from analog image to digital image, we will get like this. This is the object which we want to capture, and this is nothing but its digital conversion. Now how the analog to digital conversion takes place, or how digital image gets created. Now instead of the entire image, we can see only the AB line. Now we can see that white portion is there, then there is a transition, then there is a transition from white to black, then there is again that black is there, but after that again there is a lighter shade of black, and after that again darker shade, and after that again there is a white portion is there. Now what sensor arrays do? Sensor array captures these optical lights and converts to the electrical signal. Now this up to this A point to this point, the intensity is higher because this portion is a particular white portion, so it captures like this, or it converts electrical signal into these values. Now if you see that these values are higher than this value, after that you can see this transition. Now this transition takes place. Now this peak value is nothing but this portion where white color is there and the black color fades, and after that this particular portion is again nothing but the high electrical signal. So one represents the continuous analog signal smoothly transition between the values. Now when analog to digital conversion takes place, or when the image gets when the object gets converted into digital image, it takes place by scan, that is line by line. So raster scan order takes place, and each line it takes and converts to the electrical signal. Now only for simplicity, only line AB is shown. X-axis represents the original continuous signal, that is nothing but captured. Y-axis represents the digital signal amplitude. For example, here we capture the signal. Now we require to convert into the color. So if we want to convert into the 3-bit image, that is nothing but 8 colors, so we are using this 8 quantization level, and based on their intensity they are converted to the particular value. Now here instead of taking all that continuous value, we are taking the sample at a particular interval, and they should satisfy the Nyquist equation. Then this small circle is nothing but samples we are taking. So these samples are taken and they are converted to particular color by using the quantization. So if we use 4 bits per pixel, that is 16 colors, so here the 16 variation will be there, and according to that intensity, that is electrical intensity, that particular color is assigned to that particular pixel. So in this way the image gets created, and it is 2 by 2 array. So this is nothing but rows and columns. Spatial resolution. It refers how much detail we can see in the picture. So it's not only about the total number of pixels, but the size of those pixels. The finer the sampling process, that is nothing but the tiny squares in mosaic or grid, the clearer the details. More pixels, clearer view. The more pixels in an image has a sharper and more detail in appears. Now you can see from the example also. Now this is the object that we want to capture and the shape is polygon. Now if we use a 16 by 16 cells, that is nothing but 256 sensor array, at that time we can say that the grid size is very small and it captures the small detail of the object. So when we get the digital object, we are getting the shape very similar to the original one. But if we use a sensor array of 8 by 8, at that time maximum 64 sensors are there and this object is mapped to this. But we can see that when sensor are less, at that time pixel size increases because grid size increases and we are not capturing the final detail. Now here only 16 sensor array is there and we can see that pixel size becomes large, because when pixel size becomes large, the number of grids are total number of grids are small, so we are not getting the good quality of picture. So that is nothing but what spatial resolution is, nothing but how much detail we can see in the picture. But it's not only about the number of pixels but the size of those pixels. So when size of those pixels is small, that is nothing but grid size is small, the more number of pixels appear in that particular area. Now we can see that this is the rose flower and we can see that there is a changes from this image to this image, change is there, but we can't see with our eye easily. But from this second row we can easily find out that degradation is there. Now here this image, for example, if we see this image of 1024512, we are taking like this. See, this image is of 1024 into 104, so that much fine grid is there, so more number of pixels are here and we are getting the fine detail. Now here 512 grid size is there, so compared to this image the grid size is now large, and when grid size is large the pixel becomes big and the quality of the image gets degraded. Now this 512 is again we decrease the number of sensor array, so it becomes 256 by 256. Still we can't see any changes, only we can see the changes at the edge side. After that it is again decreases by half, that is 64 by 64. Now from here we can see the degradation of the image, and here we can't see the original object. That is nothing but here the number of pixels, number of grids are less, that is nothing but the sensor array having a very less number of that array sensor, and therefore whatever the number of pixels get captured are less and they are large in size. So when pixels are large in size, our quality is not good. So here we can see from this diagram also only 4, in that same area 16, and in that same area more number of pixels reside. So when more pixels are reside in that particular area, the pixel size is small and more number of pixels, so spatial resolution is also more. You can see easily the difference between this image and this image. This is 300 dpi, that is dots per inch, so 300 pixels are there per inch area, and here only 72 pixels are there per inch area. So when you are saying 300 dpi, that is nothing but the pixels are very close to each other and small in size, and when we are saying 72 dots per inch, so at that time pixel size is also large and they occupy that particular inch area. So when pixel size is large, less number of sample, and that is nothing but less spatial resolution, and we are not getting the fine details from the image. Now see this image 256 by 256. If we take only half of the sample, we are getting like this, and here the image degradation takes place. So when more number of samples are there, we are always getting the quality image with fine detail. Small grid size capture more detail by providing the final representation of the space. This allows for more precise analysis of variation within the data. The goal is to strike between the capturing sufficient detail and manageable data volume for analysis, because when we are taking too much detailed spatial resolution, at that time more number of pixels are there and size of the image is increased. The grid size should be appropriate for the scale of the phenomenon we are studying. So we require to take the application, we require to check that for that particular application which type of photo or which type of quality photos are required. For example, study soil moisture require the fine grid, that is a more spatial resolution compared to analyzing the rainfall patterns across a large region. Now spatial resolution tells how much detail we can see in an image. Different devices used various units to measure this clarity. Dots per inch, that is DPI. This is commonly used for monitors. Higher DPI means more dots, are squeezed into inch, resulting in a sharper image. Lines per inch, that is LPI. The measurement is more relevant for printers, especially for laser printers. It refers to the number of line printer can create within an inch, influencing the fineness of printed detail. Next is pixel per inch. This we generally use for the tablet and smartphones. Similar to DPI, higher PPI indicates more pixel pack into inch, leading to the fine detail of the image. Now here we can see that the pixel grid size is same, that is number of pixels are same, but here the whatever the background, that is size of the display change. So when the size of the display change, for example, this is the particular display area, and here the images are same, but here the more wider display area is there. So when more wider display area is there, so that particular image takes very small portion of the screen. When we are using more wider area, and when we are using this image of 256 by 256, it will come into the corner. So in this way, so here the pixel quality or image quality is same, but when we change the size of the display, at that time also we are not getting the quality display of the image. Gray level resolution. Gray level resolution describes the variation we can see in a grayscale, that is nothing but number of colors. It depends on number of bits per pixel. So it specified in the digitization step that how many quantization levels we are using. So usually it is a power of 2. The most common is 8 bit, that is nothing but 256 shades, that is nothing but grayscale image. But some application using 16 bits for even finer control over specific gray levels. More colors, smooth contour, less contrast, good quality, and more memory size. So these are the advantage with more number of colors. Less color, false contour. False contour means smooth area is not there, abrupt changes are there. More contrast, poor quality, and less memory size. Now we can see that gray level resolution is also called as tonal resolution. 8 bit grayscale, 1 bit, 2 bit. Now this is original image. If we convert this image into 1 bit, that is only 2 colors. 1 bit can store only 2 values, 0 and 1. 0 is for black, 1 is for white. So we can see that now there is a high contrast is there, smoothness is not there. But if we convert from 2 colors to 4 colors, compared to this image, now this image is smooth, but we can't compare with this image. Now as we are using more and more number of colors, and we can see that the finer detail we are getting. Now this is the image with 8 colors, this is the image with 16 colors, and this is the image with 32 colors. As we are using more and more number of colors, we are getting a continuous tone of the image. Now this is the 64 colors, 128 colors, and again we can see the original image. Now here we can see that our eye can't distinguish between 64, 128. We can see that all three images are of good quality. So that's why here the compression takes place, or compression works, because our eye is not sensitive to each and every color with equal intensity. Like spatial resolution, here also when we are implementing any image processing application, at that time also we can see that how much spatial and tonal resolution is required. Now for example, if our application is to count the car, so at that time this image is also okay. But if we want to find out the number plate, at that time we don't want such type of image, but we want such type of quality image. So it's all depend upon our application. Subsampling, that is effects of reducing the spatial resolution. Decreasing the spatial resolution of digital image within the same area result in checkboard pattern, because as less number of samples, so when less number of samples in that particular area, that is fixed area, the pixel size increases, and as pixel size increases, so quality of the image decreases, and as our grid sizes increases, the image becomes of degraded quality. So this is the area, in this area only one pixel remains. So we can see that this is the original image, and this is the image with the same area with 1 pixel, and we can't see the any detail of the image. So when we are reducing the number of samples from the image, that is nothing but checkerboard pattern occurs. Now we can see that checkerboard patterns occur, and generally first it appears at the edge, and after that it occurs on the smooth area. False contouring, that is effects of reducing the gray level resolution. False contouring, decreasing the gray level resolution of digital image results in false contouring. This effect is caused by the use of insufficient number of gray in smooth areas of the digital image. Image details are lost when the spatial resolution is also reduced. So that's why the quality of the image is based on both spatial and tonal resolution. Now size of the digital image in bits or bytes. Now it depends on spatial and gray level resolution. Now consider this is 3 by 3 image. So total number of pixels are 9 and we are using only 2 colors. Number of colors are 2. So 1 bit is sufficient to store the 2 colors. So size of the image is 9 into 1 bits. Now the same image, but we are using the 4 colors. So image value vary from 0 to 3. And here we can see that the image size is 9 into 2 because for storing each pixel we require 2 bits. Now here 8 colors are there. So to store total 8 colors are present from 0 to 7. To store each pixel we require 3 bits. So 27 bits are there. So as we can see that as more number of colors occurs in an image, then the size of the image gets increased, and that's why it's depend on spatial resolution, that is nothing but total number of pixels and how much color we are using for this image. So as we are increasing the more and more colors or tonal resolution, the size of the image is also increases. Megapixel is nothing but 1 million or 10 raised to 6. The size of the image can be defined by its pixel resolution. Resolution in megapixel is equal to column into row, that is total number of pixels of the screen divided by 1 million. Now a grayscale image of dimension 2500 to 3192, if we want to check its megapixel resolution, we have to multiply that total number of rows and columns or pixels, then we divide by 1 million and we will get that approximate resolution of the image. Now for VJ camera, whatever the program we are doing in this computer graphics, they are using 640 into 480 resolution, so that resolution is only 0.30. So when we draw the objects in computer graphics, that our resolution, that is a sampling and the number of colors or samples are on that screen, they are less, that is nothing but the pixel size is large. That's why we are not getting the fine details of circle, line or any shape. When we are using the HD TV, then its resolution is 1280 into 760. So from 0.97 from 0.9 HD TV starts. So 760p is nothing but this 180 matlab is this is nothing but the column and this is nothing but the row. So 1280 into 760. So here it is represented by 760p. Full HD TV 1080p. So this 1080 is nothing but the rows and this is nothing but columns, because when we see the monitor is always wider, that is number of columns are more. So resolution of full HD starts from 2.2. Aspect ratio and application type. The aspect ratio of an image describes the proportional relationship between its width and its height. It is commonly expressed as two numbers separated as 4:3 or 16:9. So when we see the movies in big screen, the ratio is generally 16:9. Asymmetric symmetric application. The application image and video speech, they are the asymmetric application, and because they are compressed only once and decompressed multiple times, because we capture image only once but after that we use that image for multiple times. So compression takes place only once and decompression takes place multiple times. This is same for video and speech. And symmetric is nothing but text, that is we are doing continuously compression and decompression, that is the number of compression and number of decompressions are same. Now this is the different types of resolutions are given. So it is 0.3, 0.48, this is not comma but it is a point. So when we say 640 VGA, that is 640 into 480. So at that time 480s are nothing but row and this is 640 column, but if we indicate by 480p. So this is nothing but resolution. So as number of resolution increase, so size of the screen is also increased, because there is a limit that how many pixels can reside in that particular inch area. So that's why when we are increasing the screen resolution, at that time we have to increase our spatial resolution, otherwise our image will come into the corner like this. So this is the different types of images. Now different types of images are there, but generally in image processing we are using the bitmap images. So this method that is bitmap images, that is captured using the camera, generally they are in the continuous tone, and the amount of detail can be seen in picture depends on the resolution of the image. And next are nothing but the vector images, but in image processing we are not dealing with generally with the vector images. Vector describe the shape of the object as a series of points connected by curve or straight lines, or this image is represented as internally as mathematical equation. So whenever even we zoom out or zoom in this image, we require to change only mathematical formula and it will display according to that mathematical formula. But this is not with the bitmap image. They are the continuous tone image and captured naturally. So this is all about the sampling, quantization and resolution. References used for these slides are from Gonzalez. Thank you.